Okay, in today's class we are going to discuss about the various modeling styles in VHDL. We will start by taking up examples of some styles and then continue with it in the next class. We had some discussion on what is the semantic model of in VHDL, especially we discussed the signals. We will take up a few more things today. Primarily we will talk of structural description, data flow description, algorithmic description and RTL description. These are the four main styles which are typically followed. Though the VHDL provides for mixing of these, but the designer who is using the VHDL to actually write the descriptions or write the models, he should be very clear that what is the style that he is following now, because it also depends upon what is the purpose that you are using VHDL for. As I said before, VHDL can be used for modeling, VHDL can also be used for synthesis, and depending upon the synthesis tool you use, the synthesis tool may have restrictions on which level of description or which style of description that it supports. So you have to be aware of that, and more so in case of synthesis, because there are a lot more restrictions in terms of what do you start with. So the structural description, as you will see, refers to the fact that we are describing the structure, that is, which typically is a netlist, with a netlist of components. The data flow description, we started with that. Again we take up some example where we will see that you basically have some concurrent assignments, and each of these concurrent assignments, as we said before, they all are active concurrently, in the sense that the right hand side of the expressions are evaluated and assigned to the left hand side simultaneously, concurrently. You have algorithmic descriptions. These are more like your typical sequential descriptions where you use, in this case you use what's called a process, and within the process you write the algorithm. So this description is a sequential description. RTL description typically are based on clocks, because you have already divided your algorithm or the steps that you need to carry out in terms of what will be performed in each clock cycle. So you have very clear clock cycle boundaries, and within that, within the clock cycle boundaries, you write all the transfers that you need to perform. For example, if I am describing a state machine can be described at the RTL level, because every state transition is very clearly defined to be done at every clock cycle. So you can say what transitions need to be carried out in each clock cycle, and then you can write down an RTL description. So here, the data flow descriptions could be at a very low level. You can also be writing descriptions at the gate level. Of course, when I say gate level, it's what I mean is the Boolean equations level, because if it is really the netlist of gates, then you will be describing a structural description. Structural description again could be at various levels. It could be at the gate level, it could be RTL module level structure, it could be a system level structure, where each component could be just be a, let's say a memory is a component, CPU is a component, a bus is a interconnection between the CPU and the memory, and you can write the description. And as we can use the hierarchy, we can also go down and refine each of these descriptions and go down and write at the lower levels. So this is what we describe over here. So we have several levels of behavioral and structural domains. We have several levels of abstraction, as we have just described. So we have abstractions at gate level, Boolean gate level, so RTL module level or subsystem level. Similarly, in the behavioral domain, we also have several levels of abstraction. Multiple styles of behavioral description. So as we said, behavior itself, we can write it in data flow style or procedural style. The data flow style is a concurrent description style, sequential. Procedural style is a sequential, so it's algorithmic style. Combinations, variations and special cases of these. So special case, we can describe a finite state machine in the procedural style. This is what I was talking to, where we are assigning, describing using a case statement, and we can, this case statement is executed every clock cycle. So that means a case, you basically look at the state register and then go to the proper state to execute what happens in that particular state. We will see more examples of this as we go ahead and describe these various styles. Structural description. The structural description by its very nature is a static description, in the sense that you have components which are instantiated and you have netlist among these components. So it carries the same information as the net list. What is a net list? A net list is nothing but component instances plus nets. So the net list contains the information which components are present and how are they interconnected, and the interconnections are the nets. So structural description VHDL, so on top of this, what you require in VHDL is the connections are being made. So you have one component and you have another component. The connection is being made through a signal. Because it's, as I said before, these components, so what is visible outside, the ports of this are the signals. So what you need is, additionally what you need is the signals and component instances plus port maps. What port maps does is port maps connects this signal. So what it says is this output port is connected to this signal, and this signal is in turn is connected to this input port. The signal acts as the connection between this. See, there are some languages where you actually explicitly define the nets. You say that these are the nets which are connecting. Here they are implicitly defined using signals. So the signal appears in the port map of two components. We will again see some examples and this will get clear. So it again on the port, it appears in the port map of this component A as well as in component B, but it appears in the port map of component A as an output port and on the component B as an input port, and that makes this connection implicit. Of course, this is a very simple thing, the signals, component instances plus port maps, but what we need is, because we need things like iterative circuits, we need to have, let's say, I can define a generic adder. You need arrays, because when you want to make connections between 16 bits, you do not want to keep on specifying one net at a time. So you require more structured data types, not just bits as data types. So all these things, a variety of signal types are provided to give you a structure. You have generic components so that you can actually make components which have different sizes. In VHDL, generic is used for number of features. Generic can be used for the fact that you can describe, let's say, an n-bit adder just as one component and pass this value, generic value, as a parameter. Say that I need a 4-bit adder to be instantiated, or 7-bit to be instantiated, or 11-bit to be instantiated. That is one way to use generic. There are other ways of also using generic. You can also, for example, differentiate components by generic values of their delays. I want to consider two adders. Both of them are black boxes. Same inputs, same outputs. But internally I can bind it to a different architecture. I can bind it to an architecture of a ripple carry adder. I can bind it to an architecture of a carry look ahead adder. Exactly the same interface as far as the I/O is concerned, but I can have two different architectures. And if I want to hide this fact, I can just hide it by passing a generic parameter value of the delay. I can say that this has a delay of, say, 50 nanoseconds, ripple carry adder, this has a delay of 30 nanoseconds. So I can, change this and perform my simulation completely. So this, for example, I want to really study what happens if I change this to that, and I can do that simply by passing this as a generic parameter. So the generic components are used, of course, a major use is in terms of the sizes of components that you can define. Also in terms of other parameters can also be used for generic. When you want to create multiple number of, so this is typically the iterative circuits. When you want to do iterative circuits, you can use what's called generate statements. The generate statements can generate, primarily instantiate number of components of the same type. You only want, for example, the array number to be different. It wants to you want to create 11-bit adder. So one way to do 11-bit adder is you have 11 instantiations specified, or you use a generate statement and generate. Again, we will see examples of that. The other thing is flexibility in binding components to design entities and architectures. So that's a very important thing. Like at the time, you can actually write your descriptions, and till the time you actually perform your simulation, you can leave the binding. So you can bind it only at the time that you want to bind. That is, you have the template, you have the entity, but the architecture that this particular entity will use can also be different. And even there is a notion of libraries. Typically whenever you start working with VHDL, there is a library called work created. All the things, the designs that you are doing goes into this library called work, which is a default library which is the user when is using this. But there could be other standard libraries. You can bind your components to those standard library components. Something which is available to you pre-designed, let's say a pre-designed adder is supplied as a library, you can bind it. And you could also have multiple libraries where either with multiple technologies or speeds or whatever, and then you can again choose. Some of these things we will learn as part of this course, but let me also tell you that the emphasis in this course is a fairly limited VHDL. So what will be, because the whole language is much more vast, and those of you who will actually later on do the CAD course will learn more details of it. So let me talk about the behavioral description. So one is the behavioral description is a procedural. Again, there is a point that we have made. We will see more examples of these two in the next class. The procedural description, sequential statements, and the control constructs alter normal sequential flow. These control constructs are very similar to the type of control constructs you have the constructs for conditional, if then else type of construct. There is a looping construct, very similar to the way you execute your while or repeat loops. There is also a construct for case, for multi-way branching, very similar to the constructs you have in. So as far as the procedural description is concerned, it's very similar to the way you write your high level language programs, but only thing is these procedural descriptions are permitted only within what is called a process statement. So you have to define one process, and within that process you can write your procedures. And this is sequential, and this is the only place where you can use variables, as we have. Rest of the places you have to use signals, which is a, here you can use both variables and signals, and we will see later when we see examples how do we use both of them. Non-procedural is concurrent statements. So data flow, or rather data dependency, restricts concurrency. That's important. What it means is, when we say data flow, what we essentially mean is, like we saw one example in the last class, we will see some examples today. What happens is, when you assign it to an output, when you have a concurrent statement which is A assigned, let's say B and C, and now A appears in the right hand side of another expression, so let's say A or D is E. So this is a data flow. So this is basically this. The reason that they are both are not executing simultaneously is only because of the fact that this value is required over here. Of course, this expression will be evaluated and assigned, and we will see that when if you put things like delays over here, what happens. But each time the expression on the right hand side will be evaluated. But the data flow essentially refers to the data dependency that comes when a value of A changes. Again, this expression needs to be evaluated and real E has to be assigned. So before we take up some examples in detail, let me again summarize some of the statements that you will encounter later on. We will see again examples of use of all these. Process statement is a behavior statement, concurrent procedure call. So we also have a notion of procedure call and concurrent procedure call. It's also a behavior statement. Within the process, again, you can have subprograms. You can have procedures just like you have functions in programming languages, or procedures and functions, and those are sequential. But you can also have a concurrent procedure call when you are calling the same procedure from multiple statements. And there is some restrictions on how you can use it. Concurrent signal assignment, we will see examples of this, which is a data flow. Component instantiation is a structure. But remember, when a component is instantiated, it is like a concurrent statement, because that particular component is going to be active all the time. So you can instantiate a component, and that's a part of the structural description. Generate statement is used in a structural description. Block statement is used for nesting. We will talk of that. And though the VHDL language itself was not really designed for formal verification, just like you have theorem proving in programs, by theorem proving you can actually prove whether the program will work correctly or not for the domain of data set for which you have developed your algorithm. Very similarly, today there is an attempt in hardware description languages also to incorporate verification. What they try to do is hardware. So you have designed, you have described your model of your hardware. Can you really prove that this hardware is going to be correct? In the sense that for all the inputs that you have assumed it should get, it will actually correctly produce the outputs that you want. it's not it's a fairly complex problem theoretically, and a lot of results are a lot of work is related to the way the theorem proving work in software goes off. But there is some very, let's say, preliminary attempts are made here to support something. So through what are called assertion statements. There is no synthesis equivalent for this, but what you can do is you can at places you can assert some conditions, and you can check those conditions whether those conditions are satisfied or not. For example, you have made a design where you know that at some place there will be no overflow, will never occur. The data input is so limited that the overflow will not occur. You can assert, you can check for whether the overflow occurs there or not. If the overflow doesn't occur, or if it occurs, it can flag an error, and that way you can check verify whether your design is correct or not. Okay, so that is regarding the overview of the language. Now we will actually go and study the language by taking up examples of various things. So I am not really formally going into defining the syntax, each of the statements and so on. I don't think that's required. Most of you can read that and learn that. So, but primarily we will look at various examples and we will see that how it works. Okay, so as I said before, any component that you have to think of an entity and an architecture. Entity defines the interface. We already saw that for the AND gate in the last class, the entity. So in this case, we are showing a full adder, a 1-bit full adder, and I am defining its interface. So what I have shown in bold are the keywords. So entity full adder is, so you define the ports. So there are 3 input ports X, Y, C in, and 2 output ports C out sum. The language is case insensitive, so you can write it in any lower case or higher case, it does not matter. So X, Y, C in, they are the 3 inputs, and C out. So this is for the comments. So this part just refers to that, and just put their inputs and outputs, they are the comments as far as the language is concerned. So sum and C out are the outputs and full adder. So within entity, end is the closure of this entity declaration, and this defines all the inputs and outputs. For bidirectional signals, as I mentioned before, you also have in out. Now I will associate an architecture with it, and let me take an architecture which is actually a data flow architecture, and we will spend some time understanding this because there are some issues related to it. Architecture equations of, this is just a name, I can use any name. So this is important because whenever I define an architecture, I will associate with an entity, and now I have associated that with this entity. When I associate it with an entity which has been, interface has been declared, the implication is all the ports that are declared there are visible in this architecture. X, Y, C in, C out sum, they are visible as input ports, as output ports, and they are visible, so I don't have to declare them here again. We will later on see that locally we can also declare some signals which are to be used within this description, but in this case there are no local declarations, and all the signals that were declared there are available here. What we now see is concurrent assignment, and this is we will spend some time doing that. So these are simple Boolean equations. We already, so what it says is X XOR Y XOR C in. This is the expression, and this expression is to be evaluated and assigned to sum after 10 nanoseconds. There actually that things like this 10 nanosecond timing, they are not really keywords, but they come as what's called standard packages. So the timings are defined in terms of picoseconds, nanoseconds, microseconds using a standard package, and once you have that standard package which is available to you, these are like your type descriptions and so on. So this package, so they will become available. So then this definition of nanoseconds will be defined over there. So but as far as for all practical users of your VHDL, this will be available to you almost like the keyword, but they are not really keywords, they come through this. So there is a possibility of you can define your own time standards or your own time notation if you want. So C out X and Y, or X and C in, or X and C, Y and C in. So there is anyway just the equation which defines your C out, and I am saying after 50 nanoseconds. What is the implication of, first of all, this defines my timing. This is saying that, but what is the implication of concurrency here? That is very, very important to realize. So what is happening is, I have some XYC in, XYC in, and this is your sum, this is your zero. So there is some logic over here. So there is some expression, that expression we have already said, and then this is the driver for the sum, and this is, so each of these is generating a driver. The driver is nothing but the output of this particular equation that you have instantiated, and we have associated the delay of 10 nanoseconds. The implication of this is, whenever there is any event occurring on XYC in, what do we mean by an event? An event is anything which makes a change. X, Y or C in can become 0 to 1 or 1 to 0. There is a standard bit package available, which is a 2-level value. You can also, there are also some standard 3-level or 4-level packages are also available, where you can define your data to be 0, 1, Z or 0, 1, Z, don't know what it is. So, or also you can also define some multi-level. So, that is all up to you. So, any change, so typically of course for simple descriptions like this, we just associate a 0, 1 bit type. Each one of the inputs can be 0, 1. Once you have to go for tri-state logic, you have to include the Z also. So, when an event on any of these signals, so the events are associated with signals, an event refers to the fact that X is changing from 0 to 1 or Y is changing from 0 to 1 or C in changing. So, any of these events or 1 to 0. So, if any of the events occur over here on X or Y or C in, then this evaluation takes place, and whatever is there, so that means this particular equation will be evaluated, and whatever is the result, it will be scheduled to be assigned to sum after 10 nanoseconds. So, in terms of your simulator, you assume that, so okay, so the semantics of the VHDL model comes from simulation. The language was essentially designed for modeling, so the simulator is the driving semantics, okay. So, that is the problem, that when you talk of synthesis and when you use in the lab the synthesis using VHDL, you have to be careful. So, what it means is, I make an evaluation and assign to this particular sum after 10 nanoseconds the value that I have got. So, when the simulator actually proceeds, of course, how the simulator proceeds we will see again later, not today's class, but when the simulator actually comes to this particular time, which is 10 nanoseconds from the present time, then the sum will actually get the value that is, that we have decided from that. So, similarly, the same thing happens over here. This particular, the evaluation of this expression takes 0 time. There is no time that is associated with this. So, evaluation of this expression is done, and it is again assigned to, after 15 nanoseconds, it is the, the driver assigns it. So, basically what happens is, it's scheduled to, that C out will become whatever is the value of this expression after 15 nanoseconds. So, this will be, so like these are concurrent statements, they are equivalent to defining a process with some, there is an end, I will talk of the semantics later, again another process with C out, so this is equivalent to these two concurrent statements. Data flow statements are like defining two processes, and both of them are active all the time, and when they get triggered whenever any of the inputs changes, X, Y or C in exclusive or, so X exclusive or Y. So, this expression, so any of the inputs to this expression changes, then this process gets triggered and a value is computed and is assigned to sum after 10 nanoseconds. So, that is the semantics of this statement, and that is how the, so here it really does not matter whether you write this earlier or this right earlier. What is generally what many people who learn VHDL for the first time confuses, that actually you are going to wait here for 10 nanoseconds. Please do not do, that is not the semantics. There is no wait here. That is, it is not that I am going to proceed and assign to C out after 15 nanoseconds. It's not like that. So it is, both of them are evaluated simultaneously. Order is not important. So that's just the simulator which does it. And then the assignment. Because that becomes, this type of a situation becomes important when you have assigning some expression to A and assigning some expression to A. Let's say this contains after something 5 nanoseconds and you say after 10 nanoseconds. Both of them are concurrent assignments. So when both of them are concurrent assignment, what happens is this is some expression E1, this is some expression which contains E2, which contains, let us say, A. So these two expressions are evaluated simultaneously. They are not evaluated. So the value of A that you are going to get is going to be the old value of A, not the new value of A. And with the old value of A, just because it's written later doesn't mean anything. You will evaluate the expression, assign it to B, you will evaluate the expression, assign it to A. But this assignment will be valid only after 5 nanoseconds. It will be scheduled to happen after 5 nanoseconds. Now, what happens is after 5 nanoseconds, the value of A actually changes from the whatever is the present value of A. This will get re-triggered. So the implication of this is it will get one value after 10 nanoseconds and it can get another value after 15 nanoseconds, because if the value of A changes. If the value of A doesn't change after 5 nanoseconds, then this will not be evaluated. So that is the complexity which comes in concurrent assignments. So basically so if you look at value of B, so there could be a change after 10 nanoseconds and there could be another change after 15 nanoseconds from the current time, because after 5 nanoseconds this A value changes, it will re-trigger this, and the new value may be same or and that will be assigned to it after 10 nanoseconds. Okay, you should understand this data flow statements as far as the concurrent assignment, primarily as far as the timing is concerned, to understand the semantics of the language. We are not going to use this very much. The reason is, as far as the synthesis is concerned, this timing is meaningless. Almost no synthesizer can support this type of a statement. If you, let's say I have to synthesize this statement, what it means is I have to choose components which will give me a delay of 10 nanoseconds, which is not possible. So that's not the role of the synthesizer to do that. So you actually get after you synthesize, you can get the delays depending on what you are synthesized with, but you do not specify this for synthesis. You can only specify the Boolean equation and not the delays. But delays are what VHDL provides this for modeling. If you already synthesized it, or you are going to just study how you have the models available of delays, then how this system will perform under those delays for simulation model. So now let's use that 1-bit adder and try to build a 4-bit adder. So I have this entity adder 4is, so you can see the structured data type. So you are saying bit vector 3 down to 0, so which is nothing but defining. So bit vector is the name of this. I could also have defined in my package this definition, just like you have your include files. So I could have defined a type called bit vector 3 in my package, which I could have included, where I could have defined it to be an array of 3 down to 0. So here then I would only use this shorter form, So here I am declaring it completely, which is 3 down to 0, which is an array of 4 bits. CI is 1-bit input. So I have now inputs, 2 inputs which are 4 bits, 1 input which is 1 bit, 1 output which is 4 bits, 1 output which is 1 bit. So that's the type of it's a simple 4-bit adder. And then how do I get this 4-bit adder out of the 1-bit adder? Okay, so what I was mentioning here is, if you define this, if you have to use it at number of places, you can define it before as define your own package of declarations, types and so on and so forth, and then you can, there are also types, procedures, many things that you use repeatedly, they can define it in a package and then include that package. Okay, so here, so this is again, as I said, this is only the interface, the body of it, the architecture of it we have to define, and here we are going to use the architecture which is the structure. Okay, the structure of architecture structure of adder 4 is okay, you actually need not note it down. Basically, I am going to give a copy of the chapter of the book from which you will get all of this. Okay, you will get lot more examples. So let's just concentrate on. So the whole thing is there. So that's so structure of adder 4 is. So now in this case, what we have done is I defined a component which is the full adder, which was that 1-bit full adder that I have defined before. And I have defined the signal is something which is, see, as I said before, each time I am going to associate this adder 4, please remember, is corresponds to this entity adder 4. So all these ports that I have declared are visible within this architecture. Whenever I associate it with an entity, all the ports are visible in the architecture. Now I have this component and I will instantiate 4 copies of this component. Okay, because there is a 1-bit adder and I want to make a 4-bit adder out of it. So I will instantiate 4 copies of this, and this is what I am doing: FA0, FA1, FA2, FA3. So this is all structural description because I am instantiating copies of this. So FA0 is a full adder. This is a component full adder, and I am now defining my port map. The port map essentially means, see, where does A0 come? A and B were declared as input ports. Okay, so A0 and B0 come from there. CI was also an input port, which is the carry in. C1 comes from this. So what we are doing is we are defining this so it's a structure like this. So this particular thing, what is the ripple, the carry ripple, that's where I have this signal, this carry signal which is doing that. And you can see that C1 is used over here, C2 is used over here. So this is the connection that is being made over here between the 4 bits of the adder. A1, A1, B1, A2, B2, A3, B3, they are all coming from the input ports, and CI is again coming from the input port. CO is going to the output. This is going to the output, and S0, S1, S2, S3 are all going to the output. So there are 4 instantiations of that are being made of the same adder bit. We will also see how you can also do it through a generate statement. You don't have to write 4 times because that's not required, but this is a simpler way. So now the port mappings is important because the port mappings are only what is giving you the net list. I am not saying, please remember, there are languages or there are let us say notations available, the standards available by which you say that input of this is connected to output. You give a net description. Here the nets are implicit. The fact that I am using C1 here and C1 here means that this output, this was an output port and this was an input port, they are getting connected. So these nets are implicit in VHDL. When I write my structural description, so you have to check for, so if you have to generate a net list out of it, you have to check that which output port is connected to which input port. And these port mappings, the associations are in this case by position. When I say position, you have declared this component first input, second input, third input, fourth output, fifth output, and this is again, this association is by position. There is also a mechanism by which you can make the association by names. You can, if you don't want to follow the same order as it is here, you can say that X is connected, X is associated with A0, Y is associated with B0. So those are just options of this. But if this is by position, because this position is important, because how do I know that A0 is going as an X? How do you know that Ci is going to Cin? That's because this is third position and this is also third position. So this type of association is by position. So let's take one more example of this where I will show you a generate statement example. So, this is a comparator. Okay, unfortunately, I have not made things bold, but you know that which are keywords and which are not keywords. So, comparator, we have already studied the comparators before. So, basically it is a 4-bit comparator. A and B are 4 bits and it has 3 inputs greater than equal to less than, and it has 3 outputs, A greater than B, A equal to B, A less than B. So, you look at it. So, it has 4 bits input, 3 more inputs, which is for cascading. If I want to cascade more than 4 bits, then I require those 3 inputs, and there are 3 outputs corresponding to these. Okay, let me show a 1-bit comparator data flow first. Okay, so this order I should have reversed. So, this is a 1-bit comparator data flow. So, what you have is, you again have this entity. So, here I have put both entity and architecture in one. So, you have the entity defining inputs and outputs. Here the architecture, we have written the equations. So, this is again data flow. So, they are all concurrent assignments, 4 concurrent assignments. Signal S is an. So, now you can see over here that in the previous data flow case there was no such connection, but here this S which is assigned over here is used as. So, this is on the left hand side, this is on the right hand side. So, what we said will happen. So, whenever this is evaluated and S changes, this will be re-evaluated. Okay, so that is the data flow. In this case, I have not put any delays. Okay, this is a model in which there are no delays. You can also add delays if you want to do a delay model, but here what it happen is the whole thing will happen in 0 time. There is no time that is involved in this. So now what we have is the architecture. So I am now doing that what we did before of essentially. So you can study this in leisure. There is no so there are a lot of these connections which are difficult to do, but basically you have to understand this. But I in 1 to 2 generate. What we are doing over here is now through a set of equations, I know that which is going to be connected to what. So I have generated an array, and in that this IM is the intermediate one. So what this is doing is, this is taking this 1 bit, making those 3 bits connections. This is what is. This is a 4-bit comparator which is built using 1-bit comparator. So I have described this 1-bit comparator, and this I described not as a structure but as a data flow. I have my choice. I could have described this also as a structure consisting of gates. Okay, so that's also perfectly valid. So now in this case what I am doing is, as far as the C0 and C3 is concerned, C0 and C3 correspond to these configurations. C0 and C3 I have put different statements, but C1 and C2 I have done it through a generate statement. C0 and C3 I need to have different statements basically because one is connected to external inputs and one is connected to external outputs. Others are just being connected to this intermediate outputs which are generated from one, and output of this is going as input of this. So IM0, IM1, IM2 comes from the first one, and if you evaluate this, that goes as the input over here, and then the next set of ones comes out. So you can also write through this generate statement, but all these are structural descriptions. So what we have discussed today is structural descriptions as well as data flow descriptions. We will now take up the other architectural as well as behavioral as well as RTL descriptions in the next class. So all this material is available in a fairly compact form in somebody can take this and Xerox it. So this is chapter 2, pages 44 to 84. Those of you who want to learn more about VHDL, so this is a book by Ashend and Morgan Kaufman. So both of them are available in, especially this one is available in Indian low price edition. So this one contains the designer's guide to VHDL, but it contains all the details of VHDL. So this one is what we will refer to as far as this course is concerned, where we will talk about restricted VHDL. Okay, thank you.